All right, this one I want to actually draw out by hand first. This right here is actually very similar. It's better drawn than the way I would draw it. And so they're just saying the exact same thing here, in the fact that the enzyme alters the rate, but it does not alter the overall free energy change. So the delta G for the reaction will still be the same. Okay, and also it doesn't alter the ratio of products and substrates, which is in the same way as saying that it doesn't affect the equilibrium constant at all. So therefore, the only thing that's going to be affecting is this, by lowering the transition state, the activation energy. Okay? So then we have to ask, like, how is that possible? I really hate this figure that came from your book, because it can I explain it? Pardon?
I said hate is a strong word.
Well, right, because it makes it look like the ES and the EP complex are equal in energy, and that they're also about equal to the substrate, which, by the way, if that was true, it would probably get stuck as ES or EP because of the fact that it was relatively stable. So, but I don't think, unless they changed the most recent version, that they do an adequate job of explaining the fact that it doesn't have to look like that. You can have them be higher, they can be lower, they're not going to be equal in energy. Very rarely they're going to be equal in energy. And so there's a lot of variation here. However, they do show the fact that each enzyme-bound intermediate will have a valley, and that the hill preceding it will be the transition state. And it's really, at least for me, it's kind of difficult to tell that that's really the highest peak, because it's almost the same height as everything else. But once again, the delta G of the transition state is going for the highest one, the catalytic one. It's going to be to the highest peak there. So, so for that, it's fine. But in the event that I don't think they do it justice in the fact that most energy diagrams will not look like that. Okay, and so there were the two models that we've actually talked before, especially with binding, when we discussed hemoglobin and some of the things. And the one that usually a lot of biology programs lock onto, pun intended, is the lock and key model, which doesn't show up very well in the projector. And that's where the substrate binds to the binding site, with complementary shape and charges, in the sense that it's like a key going to the lock. And so it doesn't take into account any conformational flexibility of either the protein or the substrate, for that matter, or the fact that that there could be binding energy that's required. You do usually have to put some energy in, because it's just not going to miraculously flow into there. More people subscribe to the idea of the induced fit model, which is where the binding induces a conformational change, and it's this conformational change that accompanies and makes a complementary fit. Okay, and then there's an idea that's not on here called transition state theory, which is what actually all the pictures have been and the energy diagrams have been showing, is the fact that the enzyme binds the substrate in such a way that it mimics the transition state. Okay, by mimicking the transition state, it makes it easier for that bond to break, or that bond to be, if you're adding things together, like ligating things, it makes it easier for the ligation to occur, because it's mimicking the transition state. And so there's a figure that your book uses, and that's actually what's coming up next, yes, that that they use to try to explain this. But some people really catch it with this figure, and some people don't. So I apologize right now if you don't understand this figure, because it's kind of odd. You're supposed to imagine that you are trying to catalyze the breaking of a magnetic rod or something like that. So this is the overall figure, and we're going to break it down to each individual, to blow up each individual step. And so the idea here goes, so the idea is you got this substrate, which is this metal stick. Of course, you're going to be breaking it, and so to break it, you have this transition state where it's bent. And so it takes some energy to go from it's fine as a metal stick, you have to add energy to bend it, And then it's now 2 sticks, and that would be its energy diagram. They're showing that it's no lower in energy as a product, which in some things you're going to find out, especially next semester, that's not always true. Sometimes your products are higher in energy than your substrates. So they have to be coupled to something else, or you have to add energy into the system for it to go. Let me open up my Diet Dew. Okay, so what happens here is, if this is true, this is the lock and key. And the lock and key states that the binding site would be perfectly complementary. It would be the lock, the substrate would be the key, and it fits in there, and it's all perfectly happy. Well, if that's true, and this is where it kind of gets confusing for some people, that's where they say, oh, it's magnetic. But here, let's just talk about, like, if it's charged. So if the stick, the metal stick, was positively charged, what they're saying is all of this would be negatively charged and the perfect shape. And so it's perfectly happy. That key fits into that lock and it's perfectly happy. Well, what that does is that means the ES complex now is much lower in energy. And so that's what they're showing here. You add a little bit of energy to get it to wiggle in there, but once it's in there, it's perfectly happy. And so now it's way down here and it's lower in energy than the product. And if that's true, what's happening to you're still going to have to bend it, right, to break it to 2, and then you get your 2 products. But what happened? Did this catalyze it at all? No, in fact, it makes it worse, because now the hill is even bigger than what it was before. And so that's why the traditional lock and key can't be completely correct, because the fact is, if that's true, the ES complex or the EP complex, here we're just showing one, is so perfectly happy that why would it ever want to leave? Okay, so it's much lower in energy. Why make the effort to ever leave? And so that's the whole idea of the transition state theory / induced binding. So here, for transition state theory, is that yes, it goes in, but notice it's not perfectly complementary to the substrate. It's more complementary to the transition state. And so it lowers that peak of the transition state to make the hill a little less difficult to climb up. And therefore it's going to be easier for the nucleophile or whatever to come in and break it apart. That was kind of pathetic applause for I feel sorry for them now. And so, because that's a large class, and if you only get and it wasn't even like a 1980s slow clap montage where, All right, and so, but yeah, here we now, since it's complementary to transition state, it makes it a little easier for the nucleophile or whatever it is to attack it in order for it to break apart. And now the product leaves, and all is well.
So is there a difference between the induced fit model and transition state theory?
No, they kind of go hand in hand, because technically the induced fit just means that there's a conformational change. It induces a conformational change. Transition state theory states that the enzyme lowers the catalytic, does the catalysis by lowering that transition state energy. And you can figure up the kinetics based off of, which we'll do later, but you can figure up the kinetics based off of the concentration of that transition state. Okay. So here are just some examples. This is hydrogen peroxide. Of course, believe it or not, hydrogen peroxide does occur in your body. It is a byproduct of some of the redox reactions and oxidative phosphorylation in the mitochondria in particular. Also, we have the peroxisome and things like that. And so because of this, we have to break it apart, because hydrogen peroxide would do damage if it escapes. Okay, and so you don't want that to happen. And so there are enzymes that will take care of that. It does break down on its own. So without a catalyst, here's the relative activation energy, 75 kilojoules per mole. And so then you can break this down inorganically by just using platinum, which is, for those who've already had organic chemistry, it is kind of similar to the whole hydrogenation reaction. And the platinum surface actually decreases it to 48.9. It makes the relative rate now 10 to the power 4 times faster by decreasing it by 30,000, kilojoules. Catalase, the enzyme, actually lowers it all the way down to 23 kilojoules per mole, so that hill is much smaller now. And as a result of that, it's now more than 10 to the power 8 times faster. And so its kinetic rate constant has gone way, way up. Okay, so, and they're just telling you that, this is under biological conditions at 37 degrees Celsius. So here are some of the other examples that some of these will actually come across in either this semester or next semester. So 10 to the power 5 is a modest increase, whereas 10 to the power 13, 14, 17, those are huge increases, very, very, very fast. Either that or the original reaction was so extraordinarily slow that we would die before it would ever have a chance of occurring without the enzyme being around. So some of these are involved. The carbonic anhydrase is involved in the body's regulation of its pH. Of course, TPI is going to be in glycolysis, and so it's really important for the metabolism of carbohydrates next semester. Same way with phosphoglucomutase, succinyl-CoA transferase is involved for the citric acid cycle, intermediates, urease is the urea cycle, and the aridine monophosphate decarboxylase removes a carboxylic acid group so it comes off as a carbon dioxide. But these are just to give you an idea that you can have these huge increases in the rate. This should be common sense, but there will be an optimal temperature for all enzymes. Okay, usually you get this parabolic function, and because I'm going to tell you, but at certain temperature, it's going to start to denature the proteins, or even RNA. It'll start, if you have an RNA enzyme, it'll start to denature or degrade the RNA. And so that's why, as temperature increases, it should make sense that the rate increases because, by adding in heat, you're adding in energy. And then it's going to peak, and then at some point in time, you get heat inactivation. Okay, and so there is an optimal temperature it's not always going to be 37 degrees. Okay, so for example, thermophiles, what's a thermophile?
Something that's heat.
Okay, and does anyone know what are some examples of thermophiles? Right, there are some archaeobacteria. These are organisms that also can live in the geysers and things like that, the hot water vents in the ocean and stuff, that volcanoes. So they have much higher optimal temperatures, and so we utilize them for synthesis in the lab a lot because, for example, to do PCR, we use a thermophile's polymerase to do PCR, so that way it can work at a higher temperature. Okay, so there are different types of catalysis. In most enzymes, there is a binding energy that has to be put in order to form this ES complex. And one term that's going to get used, let me do this way. For the ES complex, there is a term that I will probably say at different times, or you may even read it, since you should be working on your papers, hint, hint. And that is this. Sometimes it's called Michaelis complex. Not Michael is complex, but Michaelis. I knew where you were going with that one. Okay, and so does anyone know where does Michaelis come from? Michaelis Menten, and so they were the two that came up with a way to calculate steady state kinetics. Okay, and so the ES complex is also called the Michaelis complex. However, it's only one contributor to the overall mechanism. In fact, it may or may not be involved in the rate limiting step, because each enzyme can be different. Likewise, you have to have, the catalytically important groups that's going to either be involved for binding or recognizing substrate. It could be involved, there's some that can be involved in product release, there's some that's going to be possibly involved in the actual catalysis itself. Many, many times there's going to be a transient covalent interaction. And so the substrate may have a physical bond to the enzyme. However, it has to be released or otherwise it would be considered a suicide reaction. In fact, there are some called suicide inhibitors where they bind, they react with the enzyme, and then they can't leave. So then the enzyme is dead. Hence the reason why it's called a suicide inhibitor. And so there are certain drugs that do that if you're trying to eradicate that enzyme's action. All right, and so these are three broad classes of catalysis. First up, I want to speak a little bit about general acid-base catalysis. First of all, if you have a general acid, you must have a general base. It's like yin and yang, positive and negative. The world would end if we only had the acid, not a base. So that's why you cannot tell me, oh, this is a general acid reaction, because that doesn't exist. It has to be general acid, general base, or general acid-base reaction. And so you can look to see what the general acid is, but there must also be a base in that reaction. Okay. Now, specific acid-base catalysis involves hydrogen or hydroxide using only water. Okay, that doesn't happen very often in vivo, just because of the pH regulations. We don't have like free-floating hydroxides too often. So usually they have what's called general acid-base catalysis instead, and it's something other than water that will donate a proton or accept a proton. And so what does an acid do? What's the definition of an acid? What do acids do? They donate the proton. And so then what will the base do? Accepts the proton. And so that's why you always have to have a general, like if there's a general acid, there must be a general base. Okay, and so what are some examples before we go on to covalent catalysis and metal ion catalysis? And so what are some general acid? Oh, here, let me, probably better if I type it anyway. I'm just going to call it gen acid. Select all. Oh, where did it go? It is. So what are some examples of amino acids that could act like a general acid? And I'm just going to list.
Glutamic acid.
Okay, and its one-letter code for review is G for glutamic acid, E.
I always do.
Well, and I was going to say glutamate is also still going to be E. Okay, all right. So glutamate or glutamic acid could be a general acid. What else could be a general acid? Aspartate, and its one-letter code D. Datu. Sorry, there's like a rivalry right now going on in my hallway. Something to do with the Cowboys in the football game. Yeah.
Saints game.
Yeah, and so, they've been writing on each other's boards. Datu, the Cowboys, that kind of thing. So, all right. So what else could be a general acid? You picked the two easy ones. Something's got to be able to donate a proton. Tyrosine can be. And it's a Y. Serine definitely can be. Cysteine, and its one-letter code? C. We're missing one that's a really big one. Really biggie. I just had one student some time ago in biochemistry that used to always call it the bi one. What? I couldn't hear you. Sorry. Threonine can, but that's not the one I was thinking of, and it's the T. Histidine, that's the one. That's in use. It's a lot of times the general acid general base. And so hopefully you can see what's happening here. They just have to have a hydrogen that they can donate. Okay, so let me move that out of the way. What about general bases? Oh, I forgot to underline that as well. Oh, I meant to do that. Pardon? They can. They're not as often. Here, whoops. Otherwise, it's going to try to highlight, underline everything. But they can. So Q and N can donate a hydrogen. I'm not going to write those up for quite yet, just because of the fact that there's some that I'm wanting in particular. And we've lost our internet connection, just briefly. So acting as a general base. Remember, it just has to be able to accept a hydrogen. Lysine could. Lysine and arginine. Could they ever be a general acid? Can lysine or arginine ever be a general acid? Can they ever donate a hydrogen? Yes. Even though they're basic, they can be a general hydrogen. So that should give you a clue on what acts like a general base a lot of times. What else could be? Histidine. Histidine is the biggie. What else is there? Proline doesn't. No, only if it's the very, very, very end, because then it's going to have a free amino group or a free carboxyl group. So we're talking about just the R groups. Remember, its R group is just 3 CH2 groups that come back and hit itself.
Would it be E and D?
Right, it's all the same ones. E, D, Y, S, C, T, H. Because if they can accept a hydrogen, they can usually give a hydrogen. But yeah, E and D are used a lot. So E, D, and I'm just going to say etc. because otherwise it's going to get big.
So E, D, and H for the big ones.
Right, tyrosine is a lot of times too, especially for nucleophilic attack. Tyrosine and, whoops. Why, it's like frozen, like this is not smearing. So I do not know what, that's a new one. Huh. And it's down once again. You knew it was getting sick. It's on there, and with the Apple TV, what's kind of a pain is that you have to be on the same network, and you can only take one at a time. And so the moment it goes down, if someone else picks up the network, then you lost it. You gotta find another network. Okay. All right. So that was general acid, general base. Remember, that's just the donating and accepting of protons. Then we have covalent catalysis. What do you suppose is happening in covalent catalysis? How is that going to help lower the transition state energy or the...
So would that be like the covalent bond that forms temporarily?
Right, that's where at some point in time there is an intermediate that is covalently attached to the enzyme. There are lots of examples, and we'll see some later on. In fact, we'll see some in this chapter. There's a couple of mechanisms I want you to know. One in particular, because you're going to see it over and over and over again. And it's very important. And then there's metal ion catalysis. What do you suppose is happening there?
Metal ion stabilize or something?
Well, close. There's a metal ion, but what is it doing usually? The metal ion is actually involved in forming the nucleophile. So if you think back to Gen Chem, metal ions can coordinate to, things like water or hydroxide and things like that, and can make it have a lower pKa or a higher pKa than what it normally would have. And so you get these metal hydroxides then that will go in and attack. So this happens a lot with magnesium, manganese, zinc. Zinc is a big one.
So the metal ion actually... No, it's not,
So-
it's not attacking. So it just...
So what it is, whoops. Let me see if I can write. So you'll have a zinc, for example, and the zinc will be coordinated. They can form special bonds. So you can have a zinc water. And what it does is whenever it coordinates it, it allows for the water then to do the attacking. But without the zinc, the water cannot attack. So that's supposed to be an arrow. It just kind of looks really weird. But yep, this is one example. Okay, this is where we get down to the nuts and the bolts. The enzyme kinetics. This should be reviewed from Gen Chem. But anytime we have some generic reaction, this isn't even one that is necessarily involving an enzyme or a catalyst. So in this example here, we have two substrates, A and B, forming one product, P. Then there are three ways you can actually look. And, this is, it's a derivative. So it's from calculus, even though they don't usually tell you this. It's because it freaks people out if you use little d's. If you use a nice little friendly triangle, they're good to go. You stick a D in there and oh my gosh. No. And so, but yes, you can even look at, all it is it's the rate would be the disappearance of A, so it'd be negative change in A as a function of time, as time is changing. And it has to be, in this instance, it has to be the same as B, because it's a 1-to-1 ratio. So if 1A is leaving, it's grabbing 1B along with it. It'd be different if it was 1-to-2 or something like that. And those are both negative because they're disappearing. At the same time, product is appearing at that same rate. So that's why it's positively changing.
They give you the F and the G exponents, but they don't tell you where they go.
Pardon?
They give you F and G, the rate, as the exponents.
Well, it's because it's just letting you know that they can be variable. Okay, so the rate, every rate law, okay, let me make this smaller so I can write. There's a rate law, and I would expect you to know how to write rate laws. Every single rate law has the same, the same setup. And they have rate there, but I'm going to say V, or even a large nu for velocity, is equal to, in every single one, you'll always put a lowercase k, and it has to be lowercase k because that's the kinetic rate constant. Okay, and so otherwise, if it's a capital K, it's an equilibrium, which is a thermodynamic. Then, in this instance, you always look at the rate limiting step, and here there's only one step, so that's easy. And then secondly, you have to see what species are involved in that rate limiting step. So here's A and B. And then finally, the exponent is where they have F and G. The exponent has to do with the stoichiometry. And if you look up here, it's a 1-to-1 ratio, so technically that's a 1 and a 1. So this rate law will be V is equal to K times A times B. Okay? And so specific rate constant, kinetic rate constant, those get used interchangeably. In fact, my boss never referred to it as a specific rate constant. We always just called it the kinetic one. And the order of the reaction is literally the sum of the exponents. And so we would say this is first order with respect to A, first order with respect to B, but it's second order overall. And that tells you a lot about the mechanism. It means that 1A has to react with 1B in order to make the product. Okay, so this is the second overall. And it also affects the units for K. The kinetic rate constant units change with respect to whatever order of reaction it is. Because what must be the units for velocity, for rate? If you look up here at A and B, if you look up here at one of these, what units are those?
Change in concentration over change in time.
Right, and so usually the one that gets used the most, like the standard for us, was molar per second. Okay? So, because molar is a concentration, and then per second. It doesn't have to be that. I definitely prefer the seconds because that way there's some that will say like mgs per mil, which technically is a concentration per, 24 hours or per day, well, per day. And so then it gets really weird, some of these. But if you just do like molar per second, then it makes it easy. Notice it's molar, not moles, because of the fact that it does take in that a concentration does require some type of volume. That's why when I said mig per mil, that was milligrams per milliliter. And whereas molar already takes in that liter part. We don't have to say moles per liter per second. So that's why it's just easier. And so since every single velocity has the same units, that's why this k is really a proportionality constant, and so its units will change depending upon how many items or species are involved. So in this instance, we can actually figure out those units because we have, I'm going to use a different color, since we know that this is molar per second. And what's the concentration or unit for the A? Ooh, I just spit on the, that doesn't help. It's what? It's molar. And the one for B? Molar. And so if you have a molar times a molar, it's going to be molar squared. And so, yes, I know, thank you. Which I don't think that actually shows up in the video. And so I get to, if you ever listen to this, you get to hear me say, yes, I know, thank you. So it's going to sound really weird. Okay, so in order for this to become molar per second, what units must K be? I'm going to have to write it over here because I didn't leave myself enough room.
Inverse molar, inverse second.
Right, so K units equals per molar per second. Because that way one of the M's cancel and then the S ends on the bottom. And so that's why, and we're going to find out that for first order or zero order, or even a third order if you have one, you don't see that very often with enzymes. It's called a termolecular reaction. You do in like organic chemistry, we had a couple reactions that were termolecular, but you don't really see that really, because it's hard to bring three things in at one time and have them, do that beautiful dance of catalysis. So usually it's going to be zero first or second order. But okay, at this point I'm going to go ahead and end class. Maybe.